This is question number 57 of IIT JAM Economics 2021 paper. Let's see what the question is saying. It says x1, x2, x3 and x4 be independent random variables. So they're independent. This is important, which means whenever I will try and find the covariance between x1, x2, covariance between x1, x3 and all permutation and combination, it will always give me 0. Following standard normal distribution. This means that x1 is normally distributed with mean 0, variance 1. So is x2, so is x3 and so is x4. Let y be defined as y is equal to, so you have y and y is equal to x1 plus x2 whole square plus x3 plus x4 whole square. Now let's say that let x1 plus x2 be A, x3 plus x4 be B. So I can say y is equal to a square plus b square. Is it? So I'll keep it here only, that y is equal to a square plus b square. Now what we will go ahead and do, because the question is asking to find the variance of y, we will go ahead and say that variance of y is equal to variance of a square plus b square. But what is the formula of variance? The formula of variance, as we know, is nothing but it can be written as, so consider this as the first thing, consider this as the second thing. So if I say that, okay, I'm just taking this to simplify, you can revert it back, a square bc, b square bd, so it will be variance of c plus d. And variance of c plus d will be variance of c plus variance of d plus 2 covariance of c and d. Is this fine? Now just think for a second. What was c? C was a square. What was a square? A square was x1 plus x2 whole square. So when I say this, I'm just trying to expand this to covariance. A square comma b square. A square was x1 plus x2 whole square. Right? I just took a as this. So x1 plus x2 whole square comma x3 plus x4 whole square. Is it? Covariance. So now x1 plus x2 whole square will be x1 square plus x2 square plus 2 x1 x2 x3 square plus x4 square plus 2 x3 x4 covariance. Actually, when you will find the covariance of each with this, you will see that x1 with x3 independent becomes 0, with x4 independent. With this, these are anyways independent, independent, independent. So ideally what is going to happen, and this is something which you can simply use as a property, that if x1 and x2 are independent, then their linear combination that you create is also going to have that independence property. So, you know, when I'm saying that x1 is independent with x3, x2 is independent with x3, so x1 plus x2 will also be independent with x3. x1 plus x2 will also be independent with x4 if they're individually independent. So ideally, this entire covariance will come out to be 0. So what you will be left up with is that the variance of y will nothing be but the variance of c plus the variance of d. Now, we know that the formula of variance of anything is the expected value of c. So how do we find variance? It is variance of x can be written as ex square minus ex whole square, right? So if I have to write the variance of c, it would be EC square minus EC whole square plus ED square minus ED whole square. Now let's see this. Let's go ahead and talk about this in a bit more. So first of all, what was C? C was A square. I'll just bring it back. What was A square? A square was x1 plus x2 whole square. So ideally, this is nothing but expected value of x1 plus x2 whole square squared plus, minus expected value of x1 plus x2 whole square plus expected value of x3 plus x4 whole square minus expected value of x3 plus x4 whole square. Is this making sense? I'm just using this formula that it's ex square minus ex whole square. I'm just trying to use that same formula. So this is equal to E of x1 plus x2 to the power 4 minus E of x1 plus x2 whole square squared up plus E of x3 plus x4 to the power 4 minus E of x3 plus x4 whole square squared up. Now please see this. I will just try and find the solution of this part. This will be symmetric. I just have to replace x1 with x3, x2 with x4, and I will get the other part similar to that only. So first of all, I will just go ahead and focus on this part from here. E of x1 plus x2 to the power 4 minus E of x1 plus x2 whole square squared up. Now, we are going to go ahead and use the formula of A plus B to the power 4. So A plus B to the power 4 is equal to A to the power 4. If you're not sure with this formula, it is fine. You can go ahead and you can try it like this. A plus B into A plus B into A plus B into A plus B. In case you don't remember it, this is nothing but A plus B whole square into A plus B whole square. This is A square plus B square plus 2AB into A square plus B square plus 2AB. So you can also open this up. So, this would be A to the power 4, but plus A square B square plus 2A cube B plus B square A square plus B to the power 4 plus 2AB cube plus 2A cube B plus 2AB cube plus 4A square B square. Right? So this is the formula. So A to the power 4 plus B to the power 4 plus. Now notice here A square B square is coming here and A square B square is coming here and 4A square B square. So 4, 5, 6 A square B square. So plus 6 A square B square plus. We have covered this. AB cube is coming here. AB cube is coming here. So 4AB cube plus 4A cube B. This is the formula of the A plus B to the power 4. So this is exactly what I have to do. X1 plus x2 to the power 4. Let's take this forward now. If you ask me, if we go ahead and we say, E of, now my A and B are known to me. A was x1 and B was x2, right? X1 and x2. So expected value of x1 plus x2 to the power 4, expected value of x1 plus x2 to the power 4 will be x1 to the power 4. Expected value of, I'm just opening this up. x1 to the power 4 plus x2 to the power 4 plus 6 x1 square x2 square plus 4 x1 x2 cube plus 4 x1 cube x2. This is what will happen. This is what we are going to go ahead and get. So if we further solve this, this is going to be expected value of x1 to the power 4 plus expected value of x2 to the power 4 plus 6 expected value of x1 square x2 square. So plus 4 expected value of x1 x2 cube plus 4 expected value of x1 cube x2. Now please understand that x1 is normally distributed with mean 0 and variance 1, isn't it? So if x1 is normally distributed with mean 0 and variance 1, E of x1 will be 0. What is variance of x1? Variance of x1 will be E of x1 square minus E of x1 whole square. So this is 1 is equal to E of x1 square minus E of x1 is 0. So E of x1 square is also 1. Now these are the two things that we know, that E of x1 is 0, E of x1 square is 1. Now any variable which is normally distributed with mean 0 and variance 1, which is known as a standard normal variable, also has this property that we can go ahead and talk about E of, supposedly, and I'll come back to that property. Suppose I tell you what is E of x1 minus x1 whole cube minus mu to the power 3. So a minus b whole cube is a cube minus b cube minus 3ab a minus b. But you know, this is mu1 because I'm talking about 1. Right? So I know that mu1 is 0. So this is going to give me E of x1 cube minus 0 minus 3 x1 0 x1 minus 0. So this will be E of x cube, x1 cube. This is E of x1 minus mu whole cube. So I'm saying that E of x1 minus mu whole cube is nothing but E of x1 cube, and this is known as skewness. Right? You can go ahead and also, you know, skewness has actually a formula, but you can call this movement around mean. And skewness is represented by mu3 square upon mu2 cube. So because of this, we can go ahead and say that the skewness of any variable which is normally distributed, because its mean is 0. This is mu3 means this is this E of x1 minus mu whole cube. This is mu3, movement around mean. third movement around mean. Mu2 is second movement around mean. E mu x1 minus this whole square. So this is cubed and this is squared. Third movement around mean and second movement around mean, cubed and squared. For a standard normal distribution, this skewness is actually 0. So if this is 0, this means that mu3 square is 0. This means that mu3 is 0. Mu3 is this movement around mean. So this means that E of x1 cube is also 0. This is fine. So I'm just saying that E of x1 cube is 0. Similarly, if you go ahead and you talk about kurtosis, then the formula for kurtosis, this is given by mu4 upon mu2 square. And for any distribution which is standard normally distributed, we have the kurtosis value as 3. So the value of kurtosis for a standard normal distribution is 3. Because kurtosis value is 3, that is why if I go ahead and I plug it in this, what will I get? I just proved you that second movement around mean, which is nothing but variance, that was 1, right? This is also given to us. So this is given to us as 1. So mu4 will be 3. So mu4 will be 3 into 1, which is 3, right? Mu4. Mu4 is fourth movement around mean, which means expected value of x minus mu4. And because mu in itself is 0, so expected value of x1 minus mu1 to the power 4 is equal to expected value of x1 to the power 4. So this is also 3. So ex1, this is 3. Okay. Now let's go back and see the question. So from here, I will just pick up on this part once. And let's take this forward. So we are going to just pick up on this part. And we have just proved that because x1 is standard normally distributed, actually you should remember all this. Okay, although I've done proof of each and everything, you should remember that any variable which is standard normally distributed, it means that mu1 is 0, mu2 is 1, mu3 is 0. By these I mean that these are all movement around mean. Okay, if you don't, I mean, this is nothing, second movement around mean is nothing but variance, right? Mu3 is 0 and mu4 is 3. This is nothing but expected value of x cubed. This is nothing but expected value of x to the power 4. This is expected value of x squared. This is expected value of x1. These are actually the properties of any variable which is standard normally distributed. No need for this entire proof. You should remember these properties well. So now, because x1 is standard normally distributed, so e x1 to the power 4, which means this is 3. So I get 3 here. Plus e x2 to the power 4 is also 3. Plus, see, x1 and x2 are independent variables, right? So because they're independent, I can rewrite this as 6 e of x1 square x2 square can be rewritten as 6 e of x1 square into e of x2 square. But x1's e of x1 square, which means this is 1. X2 also has the same properties as x1, so it will also be 1. So this would be 6 into 1, which will be 6 plus 4. Now, if we go ahead and we take it here, this is going to be 4 into E of x1 into E of x2 cube. But E of x1 is 0. So into 0. And this is going to be 4 into E of x1 cube minus E of x2, which would be 0. So what I'm going to get from here is going to be 6 plus 6, which is going to be 12. This is what we would be getting in this case. So let's go back and let's just check this. What we have done till now. So we have got, we were going ahead and we were trying to find out this part. We've just done this. E of x1 plus x2 to the power 4. This has given me 12. This has given me 12. Now, if I go ahead and I, try and solve this part. E of x1 plus x2 whole square squared up. Let's solve this now. So we have E of x1 plus x2 square whole square. This would be E of x1 square plus x2 square plus 2x1 x2 whole square. So this would be E of x1 square plus E of x2 square plus 2E of x1, E of x2, because they are independent, whole square. So this is going to be E of x1 is 1. I just told you that any normal variable, any variable which is standard normally distributed has E of x1 as 0, E of x1 square as 1, E of x1 cube as 0, E of x1 to the power 4 as 3. So plus 1 plus 2 into 0 whole square. So this will be 2 square, which would be 4. So this is going to be minus 4. So 12 minus 4. Now remember that I just told you that this is symmetric. Whatever value you will get from here, because just you're changing the variable, but the variable have exactly the same properties. So this is also going to be 12. And this is going to be 4. Right? So minus 4. So this will be 24 minus 8, which would be 16. So the answer to this question should be 16. So although I spent a lot of time in proving a lot of things, which is not required, but you should just remember certain properties of a variable which is standard normally distributed, and I will list them down again. So any variable which is standard normally distributed has E of x1 as 0, E of x2, E of x1 square as 1, E of x1 cube as 0, and E of x1 to the power 4 as 3. Its skewness is 0 because it cannot be skewed. It is normally distributed. Normal distributions are bell-shaped, and kurtosis is the perfect kurtosis, which is 3. Okay. Okay. Thank you.